Yes, I'm sorry about that. When I was adjusting this slide earlier today, I couldn't believe I'd given you such a stupidly long title. But anyway, so first thing I want to do is correct a typo. I'm not actually from Imperial College, but in fact Imperial College, like most of the rest of the people who seem to have been talking to you today. And also actually from Stockholm University as well. So because this is for once a sort of methodologically themed meeting, it means, whereas mostly when I give talks like this, people are most interested to hear about the Hubble constant and what we know about it, I'm going to focus on what I think people are more interested to hear about here, which is the Bayesian analysis aspect of this. And so what I've done here is taken a dot product of the title with my own expertise, and you can see the neutron stars have kind of faded out there. I really don't know very much about them at all. So if you want to know about the details of quadrupole radiation from binary neutron stars, ask someone else. But if you want to know about particularly Bayesian analysis of astronomical catalogues and the Hubble constant as an application, ask me. And please feel free to ask me during the talk. I'm kind of, these days, much more in favor of conversations than presentations. So just to give a little bit of a summary and motivation for this, not really what I'm going to talk about, but you've possibly seen plots like this before, which makes a lie of the name Hubble constant, because whatever's happening here is, at least observationally, it's not so constant. It's been wavering around all over the place. And there are some people in this room who'll remember these sort of pitch battles about whether it was 50 or 100 kilometers per second megaparsec. And then in the last, decade really, things seem to have sorted themselves out, where if you make local measurements using an increasingly rung-free distance ladder, which is essentially these blue points here with the error bars, and particularly the shoes project, then you get a value of about 73 kilometers a second per megaparsec. Where if you take a different approach and you look at the cosmic microwave background, which we heard about earlier today, and extract the Hubble constant out as one parameter from that analysis, then you get actually a significantly lower value here of something like 67 kilometers per second. And given the error bars on those two respective measurements there, it turns out that we've got something like a 3.5 sigma discrepancy here, which is just right at that sort of area where the statistics are starting to excite people. And to give a bit of context for this, for why I'm going to talk about neutron stars, this purple error bar here, normally I'm used to the dot wobbling around because I'm nervous, but the screen's wobbling around because it's nervous. This purple point with error bar here is the result from observations of a single merging neutron star, GW 170817. And obviously it's not competitive and can't resolve whether the high or the low value is correct, but that's just one single astronomical object, whereas, for instance, these measurements here from shoes involve something like 3,000 distinct astronomical objects, and obviously the CMB isn't an object as such, but it's the entire sky. So I think that's, that summarizes why people who even don't do gravitational waves are excited about this possibility. Yes.
So aside from the discrepancy,
Mm-hmm.
the statistical significance you quote for the discrepancy is entirely driven by the shoes error bar.
Almost entirely, yeah. So, you can see it actually a bit better on the next slide, that here the vertical axis is the same as before. It's the Hubble, the actual axis itself is the same as before. That's the Hubble constant, the current value. And then if we go back to higher end redshifts, that's the Hubble parameter with a convenient 1 plus z scaling included that shows how this evolved and hypothetical aliens in the past might have measured it. And so, yes, the value extrapolated from Planck to the present day, assuming flat lambda CDM, is here. And those of you with good eyesight will be able to see an error range there. And I think it's about 0.6 now is the current uncertainty. And then this is the shoes result here, much higher, and has an error bar approximately 3 times the size. And so the statistical discrepancy between these two measurements is, the significance of it is dominated by the size of this uncertainty here. So if you weren't worried about systematic errors at all and just statistical errors, what you would like to do is reduce that upper error bar. The other thing I was going to say in this slide, this is also, I think, while people are excited by this, not just some vague notion that there's a problem that we might have to solve, but there's three basic classes of explanation. One is that there are unaccounted for systematic errors or modeling errors in this data set, the distance ladder. One is that there are unaccounted for modeling errors or systematics in this data set. And then the third is that this extrapolation here, i.e. flat lambda CDM going from redshift 1100 down to redshift 0 is wrong. And of course, that's tremendously exciting. That's another one of these sort of moments where if that were true, our cosmological model would need revision. But personally, I think it's a long way premature from doing that, but that's the possibility that's really excited people. So the first thing, a little bit of a detour from the main topic I was going to talk about, is just given that this is the motivation here, and I threw up that little phrase 3.5 sigma, and given that I'm being Bayesian about everything I do here, and it seems that that is the general flavor in the room as well, it's worth commenting on what that 3.5 sigma means. I mean, anyone who's been through an undergraduate physics degree has at some stage quoted something like that in a lab report. But in terms of interpreting it, what I think we want to turn that number into is some sort of statement about the probability that we think that those two values really are truly different. And the moment you're talking about that, you're talking about a Bayesian interpretation of probability. This slide isn't really designed for you. I think everyone here has seen this equation before. But this is just a very simple reworking of that equation to make it appropriate for the situation at hand. And being a statistician, my first reaction to this is, what are the chances that what I want to do here is phrase this as a hypothesis test, and any statistics textbook will have null hypothesis tests, and the null hypothesis will be called H0. And unfortunately, H0 is used. I mean, 1 in 26 chance of the letter, and maybe double that if it's capital and lowercase. Subscript could have been anything. So unfortunately, the two parameters I want in this talk have both got the same natural name. So I'm going to call my null hypothesis M0 for the null model. And all this is taking Bayes' theorem and calculating the probability that that null model is true given whatever data I've got and inevitably some prior information that I'm going to assume is the case. So you just take Bayes' theorem, divide both the top and bottom by the same factor, do a little bit of algebra, and particularly if the null model is fitting badly, then you get a comparatively simple formula here where you've just got a prior odds ratio that should be at least half if you're genuinely considering it a null model, and then a ratio of likelihoods here. The top one is just the likelihood of getting the data you have seen under the null model, and it's good that that appears. It would be very strange if that likelihood wasn't in there. And the first important thing, which again I realize many people in this room know, but a lot of people sort of seem to, forget maybe, is that this probability that the null model is correct is just proportional to this, again, assuming it's reasonably low. There's no tail probability here, and there's no hint of a p-value. You would never calculate, at least starting with Bayes' theorem, the probability that the data is more unlikely than that you've seen. You're just interested in the probability of getting the data that you've got. And generically, for anything with a Gaussian-like tail, this means the level of discrepancy you get out of this is less dramatic than you might think if you were going to compute a tail probability. The second ingredient here is the probability of the data given m prime, where m prime is an as yet undefined, in fact, alternative model, because the moment we're even considering doing this calculation, there's got to be some alternative that if the Hubble constant isn't the same from these two measurements, then something else is true, even if we don't know what that is. And so I'm going to just talk now about what happens if you try two different approaches to dealing with that lack of knowledge there. And the first is from a paper by Stephen Feeney. Well, Stephen Feeney is the first author, more to the point, who has done a huge amount of the work that I'm talking about today. And if you're looking for a promising young cosmologist and astrostatistician, I think he's certainly worth considering. And what this is showing here is, again, the Hubble constant just divided through by 100 to make it dimensionless. And that is the likelihood from the CMB. And something like this is the likelihood from the shoes data. And if you consider the possibility that your alternative model is that actually there are two different values if you evaluate the Hubble constant or its equivalent at high and low redshift, then the alternative model to the null is that these two values are different here. And if you go through the mechanics of Bayes' theorem, whether that's more likely or whether more probable or not comes down to integrating the product of this curve here with this curve here. And if these things are all Gaussian, then it's possible to translate the answer to doing that integral and make it a function of the number of sigma discrepancy, so a function of the 3.5 sigma. But if the tail of this distribution here is not well described by a Gaussian and is either heavier, as in this case here where we have, sorry, the colors don't quite match up here. This is where you have a student distribution in some of the outliers in the objects that don't quite fit the distance ladder well, which are currently pruned, or the difference between the purple and the yellow is essentially just whether you're assuming something is Gaussian in a linear variable or a log variable. And they don't do anything to the overall estimate and the error bar that you quote, but they do a huge amount here, change by an order of magnitude the height of this tail at the point that the local distance ladder likelihood goes through the CMB fit. And because the CMB error bar is so small, the value of this integral, when you're doing this model comparison, is primarily determined by this height here. So this is, I think, a real trap when you're talking about n sigma discrepancies, 3.5 or whatever else it might be, is that the tendency is to think about the discrepancy as what would be a horizontal measure on this plot. How far this peak is from this peak. An occultation, excellent. This peak from this peak, normalized through by the relative error bars. But that's, in this case here, when there's a reasonable separation, that's not what determines this. It's the height of this tail here. And so if you assume things are Gaussian, then you drive, in this case, the height of that tail to be particularly low. And so what this work was about was trying to assess that for sure, whether there really was good reason to believe that far from the central fit in the local distance ladder that this tail was Gaussian. And so we did a model where we, rather than taking the approach of the shoes team, which was to cut outliers from their fits, particularly from the Cepheids and the supernovae, we modeled them with heavier tail distributions, so we didn't have to cut anything, and then the tails adjusted themselves. And it turns out that the level of discrepancy here is nothing like the nominal 0.0007 that you would get if you took a p-value from the 3.6 sigma, and actually the sort of posteriors you'd put on the null hypothesis are in the sort of few % range here, depending on which of these values you'd take. So there's still, the discrepancy doesn't go away, that's not a suggestion of that, but the level of the significance is much lower than you might think naively. And a related aspect of this is just another way of trying to look at the same problem that goes away from these tail values here, and this is using something called the posterior predictive distribution, which my sense is that has become a complete standard technique in the statistics world and hasn't actually sort of risen up too much in the astrophysics world. And so all this is a way here of saying, okay, what I want to do is combine my two sources of uncertainty. So there's the narrower uncertainty from the highly precise CMB measurements, and then that gets convolved with the much broader uncertainty from the local distance ladder. And that says now, if I take the CMB value for H0 to be true, and then combine those two uncertainties together, what that gives is a prediction for the distribution of measurements that I would get, as in best estimate measurements that I would get from the local distance ladder, given not only its uncertainties, but also the uncertainty in the CMB. And then the point is to evaluate that at the position here of this vertical line, which is the measured value from the local distance ladder. And the key statistic that comes from this is essentially the ratio, again, of its heights, not distances that matter. It's the ratio of this probability density here at that measured value to the peak, which is the best you could possibly do. And again, rather than being values down sort of into the 10 to the minus 2, 10 to the minus 3, instead we're talking things that are sort of around the 5% level, depending which data combinations you take. So that's just a little sort of pre-tour of some aspects of what happens when you apply Bayesian inference to this particular problem. And then now I'm going to, for the sort of second 3/5 of my talk, talk about the main topic here, which is now this sort of methodological point looking in using binary neutron star mergers to measure the Hubble constant, and particularly the analysis at a catalogue level and what biases you have to look out for and how the Bayesian analysis that is fairly standard in this field now deals with them and yields you estimates of the Hubble constant that are both accurate and precise. So you get the small error bars that you expect and they're error bars that you can rely on. So this is just a quick summary here of how you actually get the Hubble constant from a binary neutron star system, or in this particular case here of GW 170817. And the key point about this particular system is that we got quite a lot lucky, not just in discovering a merging pair of neutron stars reasonably close to us with a very high signal-to-noise detection, but then once LIGO made that trigger, it turned out that a burst, or decaying burst in the electromagnetic spectrum was detected, and very soon after that, a fading afterglow, which meant that we had a precise location in the sky for this object, which the gravitational waves don't give you. So that for one thing, that improved what we knew about the gravitational wave emission, the intrinsic emission. And then the second thing is that it meant that we could go and get a redshift for the host galaxy in which it turned out this merger had taken place. And so that means that you've got an object now where the gravitational waves give you a distance with no distance ladder whatsoever. There's obviously an assumption of general relativity, but there's no building up from anything local like parallaxes, etc. And then you've got a redshift for this because of the fact that you've been able to take a spectrum of the host galaxy. And so you get the Hubble constant from that by the fiendishly complicated method of dividing that redshift by that distance. And what you get for that single object is that error bar I showed you in purple earlier, which is 70 kilometers a second. So the best estimate from this is smack bang in the middle of the two current competing values. But with obviously much larger error bars. So that's the basic methodology here, and that's, as I said, from a single object, which is quite remarkable. Although if you told someone from a different scientific field that we spent hundreds and hundreds of person years and billions of dollars to measure the distance to an astronomical object to sort of 20 or 30% accuracy, perhaps they wouldn't be so impressed. But that's what we're stuck with. It's a big universe. So the way this works is that as the binary neutron stars get closer and closer together, they have what's called a chirp signal, where the frequency increases at the same time as the amplitude increases, and then to a point here where actually this nice linearized general relativity model breaks down because the two objects merge. And if you look at the LIGO and Virgo data for this object, and you were just to plot a time stream, the sort of thing you might naively do, then you don't see anything. But if you do a matched filter, you get this beautiful thing here where, especially there in the LIGO Livingston data, just because of the orientations, You get this lovely curve here that precisely matches the prediction where the frequency goes up as a function of time, and then that's what you're measuring with the in-spiral of these two neutron stars. And the reason that this works as a distance indicator is that just that time dependence gives you very tight sub% constraints on the redshifted chirp mass. So that's 1 plus z times a very simple combination of the masses of the two objects. So this quantity here, which gives the strength of the signal, is empirically determined by the time dependence. And then the other quantities that enter into the strength of the signal are inversely the distance here, which is obviously what you want to measure, and then some very simple functions of the inclination, basically the angle between the angular momentum vector and the line of sight, so whether the system is face-on, face-off, or edge-on. And it turns out that possibly, if you, depending how well you believe the physical mechanisms for the radio emission from systems like this, that actually allows you to break this degeneracy by singling out here a fairly narrow range of these inclinations. Theta obs here is what I've called I in my plot. And that takes this degeneracy that we've got here from GW 170807 and tightens it up, and hence tightens the distance range on that as well. But for a single object like this, I think that's probably a reasonable thing. But given that we're trying to sort of, the ultimate aim at the moment at least is to settle this debate about the high or low values of the Hubble constant, I would instinctively myself prefer the numbers game and introducing as little modeling uncertainties as you can. So for the rest of this talk, I'm not going to talk about this possibility and just the case where it's the gravitational wave data alone. Yeah, so that summarizes the situation there. This is what that single object tells us from the gravitational wave data as compared to the CMB and the local distance ladder. And the question is now, if we get 10 or 100 of these objects, how will that allow us to resolve this discrepancy, and what's the sort of formalism for doing that? So to give a feel here for what numbers that we can expect, if you just take a sort of simple linear error analysis, then you get values like this, an uncertainty of 3 kilometers a second for a sample of 10 objects for canonical values of the measurement uncertainties and the distance to the samples. But you've also got a couple of potential systematic errors as well, which is what really is the focus of our analysis. Plenty of previous work had looked at this term here, and we were interested in focusing on the bias or the potential biases here. One of which really motivated the work was the selection bias, the fact that the same data that determines whether you identify this event and include it in your sample is the data that gives you those amplitudes and hence your distance measure. And this is just a feel here of what happens. It's this green curve here is what one can expect. This is from a paper just about to come out or just about to be published. It's been on the archive for a while now by Chen et al., where between 10 and 100, your percentage error here in H0 is getting down to a sort of a few percent level. So at least, you know, if the data are good enough to achieve this, then that's our possibility that, you know, this data will be able to do it. And then in the rest of this talk, it's about how Bayes' theorem allows you to extract this data in the right way. So we've already heard about Bayesian hierarchical models. So just to get a sense, who here has actually used one? Okay. But who here has heard of them? So I think you're lying, because if you came to the last talk, you've heard of them. Anyway, so what I was going to do here was try and walk through the Bayesian hierarchical model for this problem in a way that actually makes it sound less Bayesian and reveals what I really like about them, in fact, is that in setting one up, you're doing what almost all of us have done if ever we've simulated astronomical data. So if you've ever simulated what you might get out of some data set, that means writing a computer program where you do obviously lots of Monte Carlos to get the numbers of objects and their properties, and the flow chart for such a program is what you have to do to set up a hierarchical model that you can then choose to analyze using Bayes' theorem to go back in the reverse direction and start with the data and get statements about the parameters. So for this one here, there are two true priors that come into this model. The first is on the binary neutron star population itself. So this is things like the mean and the range of chirp masses that you expect, and possibly the redshift evolution of the rate of these mergers, although fortunately we're looking at such low redshifts that there can't be that much evolution. And the other prior that comes into this is the prior on the cosmological parameters. And it turns out you do need to include more than just h0, even if you're going up to moderate distances of a few hundred megaparsecs. But you can think of that here as h0 as the key thing, that if you're going to be estimating it and you're going to use a Bayesian method, then you're going to have a prior on it, whether you like it or not. So that's kind of the initialization step of your program. And then the next thing, if you were simulating the data, is you'd say, okay, well, I've got priors on these things, and I'm going to make a draw from those priors, and they will give me the actual population and cosmology parameters for the simulated sample of objects that I'm going to make. So this is just a draw there on these two things. And one thing that comes in very early to this process here, and I want sort of hardwired into this right from the start because it's what we're interested in investigating, is that before we even think about the populations involved, there's going to have to be some selection criterion. And it's not strictly the case, but certainly in extragalactic science, the only reason that we have finite object catalogues is that we have selection criteria, flux cuts or whatever else it might be. This is what ensures that we have finite data sets, even in a potentially infinite universe. So the next thing is, having decided randomly on what population parameters and what cosmological parameters we get, then you have to make a whole lot of these binary neutron stars. And so they're parameterized by several things here. The theta is their own intrinsic parameters, spins, masses, etc. Redshift is obviously the key thing that determines how far away they are, and I have to be careful to sort of not say distance. Redshift here is just the cosmological radial coordinate, and the reason that you have to be a little bit careful about that is that also they will have a peculiar velocity, which particularly for the most nearby objects will matter in terms of this inference. And also I've separated out here the inclination because we really know what the prior on inclination is. We believe these things don't know where the Earth is. And so it kind of feels tempting there that without doing anything with data, I could just make a realization, draw a whole lot of intrinsic parameters, redshifts, inclinations, and velocities, and make 100,000 of these and use that as my sample of binary neutron star events. But in general, that's not enough, because if we have a model where these things, neutron stars were merging, say, out to redshift 1 or redshift 10 or something like that, and I'm thinking about the current LIGO and Virgo samples, which are only sensitive out to redshifts of sort of 0.0 a few, then what's happening here? It's no use making those objects out to higher and higher redshifts. And of course, what's happening is that that plate there in red, which, everything inside that red rectangle here is a single object, is that, sure, everything here is a neutron star, binary neutron star event with intrinsic parameters, but to get into our sample, it has to satisfy the selection criteria here. And this is why when we simulate a sample like this, even if we have an unbounded infinite model, that hitting that model with selection criteria, where you take the parameters, add noise to get particularly the gravitational wave data on which the selection is based, and if that satisfies the selection criteria, you keep the object. And so this is a vitally important part of simulating this sample here. And even though I've tried to phrase this in terms of a graphical model like this, I suspect that there are lots of people here in the room who've written software that roughly does something like that. make lots of realizations of a population, add noise, and then subject that fake data to a selection criterion. And the result of that is these things in these double circles at the bottom here is two distinct things come out of this. The first one is that you get a certain number of objects coming from this process. It's not in general deterministic. It's going to typically be something like a draw from a Poisson process, something I'll come to in a second. And then for each of those n objects, well, in your simulation where you're omnipotent, obviously you know their true parameters, but for a real data set, obviously you only know their measured parameters here. And so that's your full data set, is this number of objects that you've discovered and the measurements that you have of them, subject to the fact that in this case here, the gravitational wave data has to satisfy a signal-to-noise criterion defined by ρmin that selects it into the sample. So that describes how you would simulate a data set like this. And the really nice thing, I think, is that that description of a forward simulation, written here as a graphical model, so kind of like a flow chart, is exactly what you use to do Bayesian parameter inference, where the only difference there is rather than going down from the top, as I did, we want to take these things at the bottom, the data, and actually I should have really included n in the lovely pink shading, and take that and then go backwards, and in particular here, work out what your posterior is on your cosmological parameters. And so, of course, the mathematical way of doing this now, going back into sort of the algebraic world, is to do this using Bayes' theorem. And I'm not going to go into the mechanics of how to turn a graphical model like that into a posterior, but the only two key parts of this are that graphical model gives you effectively the joint posterior in all the parameters. So in our example here, not just the cosmological parameters that you care about, but you're simultaneously estimating the true properties of your n binary neutron star mergers and the population properties and the cosmological parameters that you care about. And then the second part is the thing, I guess, that makes Bayesian inference so great in terms of nuisance parameters. If you can get hold of this, then you simply integrate out the things you don't care about, so the properties of all the neutron stars and their population, and leave the parameters that you do care about here. And actually, I've got my indices wrong there. I should be integrating from m+1 to n. The joys of LaTeX. And if you do that for the model that I described, for the neutron star population, binary neutron star population, then what you get here is a synthesis of formulae that have become pleasingly quite standard in the gravitational wave literature. It's the only sort of subfield, I guess, of astrophysics where this seems to have been adopted as the de facto standard within the field. So these papers here that particularly Taylor et al. And then Mandel et al. 2018 is an interesting one which shows how standard this has become. In the abstract of this paper, they say basically they wrote this up and submitted it to the archive because they were sort of sick of people pestering them to, can you show us how that works again? And it's like, right, we're going to write it down properly because it's been so much lore in the field. So most of these papers here have concentrated less on the counterparts, and then the LIGO and Virgo and then Chen et al. Papers have added in this part here with the idea that you also have redshift measurements and peculiar velocity uncertainties. So obviously I'm not expecting you, I'm not going to test you on this, there's no exam, but what I want to show is that all the ingredients that you'd hope are in this equation are in fact there. So it's the joint posterior and everything, all the properties of all the binary neutron stars and their population and the cosmological parameters, and then the data includes how many objects you got, the measurements for each of the objects, the property of the observations, and the prior. So it's kind of a list of everything that goes into this calculation, and it's a long list. But then what comes into this is all the different sources of data that you're bringing to bear on this problem. And actually, it's easier to sort of start at the end here and work backwards, which is everything that's in this kind of purple box here. All that is the information that you have about the redshift of the host galaxy, independent of the fact that it's hosting a binary neutron star. So you've got, measured spectroscopic redshift. If you're lucky, you've got an estimate of its peculiar velocity, but that might be very noisy or untrustworthy. And you've got some measure of what you expect the peculiar velocity of these galaxies to be, given that they're part of cosmological structure formation. So all this is saying, that's what I know about the redshift of the host, one part of that ratio that gives Hubble constant. Then this part here in the longer blue box is everything that you know about the merger event itself. The one thing I've spelled out here is that you've got a sinusoidal distribution in the inclination, again, because effectively you're saying they're pointing in random directions. Then you've got a prior, for my model of the population tells me a priori how likely different mass ratios and so forth were. And then the heart of it, the actual data you want to use, is the probability of getting the likelihood for the gravitational wave strains, and depends on, sure, the properties and the inclination, but in particular here, the luminosity distance to the system. So all those different sources of data are in here, and in a unique way that Bayes' theorem specifies. And then if you look at everything in that bottom line of that equation there, everything's got a subscript I, because this is a product over each object in your sample. So it's the Bayesian equivalent of averaging, the sort of thing that scientists naturally do when they've got a bunch of equivalent measurements of equivalent things, but here again in a particular way that follows the laws of probability. But one thing, it's a bit hard, I think there's no hope of seeing this for the first time that you'd actually notice this, but now I'm going to assert that nowhere in this second line here does the selection probability come into it. The fact that I said that it was vitally important that this is an analysis of a selected sample where every object in your sample, the data, has to satisfy the signal-to-noise criterion, which typically means that you'll get stronger signals on average because you're biasing your selection. That gives you lower distances and hence higher values of the Hubble constant. And it turns out the only place that enters here is in this exponential term, which is e to the minus expected number, and the expected number of objects obviously does depend on selection because it's the expected number of detected objects. And it might seem a bit arbitrary that this is exponential, but what this really is the leftovers of a Poisson distribution that was out the front of this. And after some cancelling, you get this exponential term here. And things wouldn't make any sense at all if you didn't have this, because if you took away this term here, then you could just make all these other terms as high as you like because you're not forcing your sample to be normalized at all. Whereas what this does is that if you change the model in such a way to increase the likelihoods here, what will happen is that you'll predict way more objects than you see, and this term will penalize that because it drops off exponentially with that expected number. And then finally, the priors that we put on our actual true parameters have made it all the way through to the end here. So this is what happens if you assume a Poisson model for this system. And if you go and analyze this, then I've just got 3 more slides, so I think the time's okay. You get plots like this. So what this is showing here, each of those panels is for samples of binary neutron star events of a fixed size. So single events on the left all the way up to samples of 100 events on the right. And what in each case, if you pick a curve of a particular color, then that's plotting the posterior distribution you get in H0 marginalized over all those other parameters using this model that correctly accounts for selection. And the point of this is twofold. Firstly, that you see as you get to larger and larger samples of events that this posterior becomes Gaussian itself. So it's the it's the Bayesian equivalent of the central limit theorem or asymptotic normality. is something that is actually coming in comparatively early. It's almost true at n equals 10, and by n equals 100, you could happily approximate any of these posteriors as a normal with a certain mean and a certain variance. And it's starting to look like this is potentially unbiased in the sense that there's as many to the left as to the right. And even though bias in this sense isn't something that really exists within Bayesian inference, you can do a near enough equivalent to this, which is to repeat that process that I did 25 times to get each of those curves in the previous plot. And now we do this, I don't actually remember what the number is, it's several thousand times. And so you simulate a sample, subject it to selection, analyze it, get the posterior distribution in H0, and then for each posterior distribution, characterize that by either the peak of the distribution or a mean, it doesn't really matter, and then make a histogram of those values here. So it's kind of the equivalent of what a classical statistician would do to see whether an estimator was biased or not. And already things are looking okay, even if you just have a sample of one event. But what we're really interested in is this case here where we've got 10 or 100 events. And so you can start to see there that not only are the posterior distributions becoming into the asymptotically normal regime here, but actually the histogram of best estimates you get is first of all unbiased, secondly reasonably well approximated by a normal, and third predicted by what you'd get. This curve here is essentially what I got from the linear error analysis right at the start of or actually about halfway through the talk. So even though the selection sort of biases the individual properties of the particular events that you're measuring, you analyze it in the correct way, and you get exactly what you would expect if you were doing this naively and weren't subject to selection at all. So it really does take it away more or less perfectly. And so that's what we hope we might get, I guess, somewhere between sort of 5 and maybe realistically pushing out 10 years from now. If we have 100 binary neutron star events and with counterparts, then this is the sort of distribution, or if we go back, any of these is the sort of posterior distribution you'd expect to get from a single event. And if you compare that to the current CMB and current distance ladder data, you can see that this really does have the possibility to solve that battle if it in fact is still going on 10 years from now. So that's where I'm going to finish.